Okay, so class, you can see the slide, right?
Yes.
Okay, thanks. Okay, let me check. Sorry. Recording. Okay. Yeah. So this topic is electromagnetic induction, still about magnet. But the one you learned before is motor. Okay, you learn about motor, the last previous one, electromagnet. This topic is generator. So motor, generator. What's the difference? What's the difference between motor and generator? Motor, for the case of motor, sorry, I can write, yeah. Motor, what two things you have supply, what you get? In generator, also another two quantities you supply, you get the third quantity has been created. Motor, what plus what do you get? Do you apply force for the motor? No. You supply current to the motor, and inside the motor you have a magnetic field, a bond magnet inside the motor. So current and magnetic field, react, produces force. This is motor. The direction of force, we use Fleming left-hand rule. Generator, what and what you apply, what you get for generator? It's exactly the same. These three quantities, just the other way around. Okay, we apply force. Hydroelectric dam, the water pushes the turbine. So the generator has been force is applied to the generator. Okay, then what happened? Inside the generator, it has its own magnetic field and create current. Instead of current, it create voltage actually. It create voltage. If it's a closed circuit, it create current. Okay, I put a current here to simplify. So this topic 10, electromagnetic induction, is about generator. How do we produce current? Or in other words, how do you produce voltage? By using force and magnetic field strength. Okay, I believe your early studies you learned about generator, but we're going to do in depth about this now. This is called electromagnetic induction. Induction means producing voltage from electromagnet, the magnetic field. Now, from electromagnet, we produce voltage. It's called induction. Okay. Two scientists contribute to this development of generator. They are law based on. Okay. Yeah, very short. The learning outcome. Okay. Okay. The first thing, we need to understand something called magnetic flux. Okay, this is the first quantity will be introduced in the induction. Magnetic flux. What is magnetic flux? The flux is defined as, the magnetic flux is defined as the penetration of magnetic field strength through an area. It's a product of magnetic field strength and a cross-sectional area. And the magnetic field strength must be normal to the surface area. Okay, so flux is defined as the product of magnetic field strength normal to the area and the surface area. Okay, you must say, you don't just say flux is the product of magnetic field strength and the area. You must say the flux is the product of magnetic field strength normal to the area, normal to the area and the surface area. It's called flux. Okay, symbol is phi B dot A. B magnetic field strength. What is the unit for B? Of course, we know B is Tesla. B is Tesla. And A, of course, meter squared. So the flux become Tesla meter squared. I got one special name, Weber. The unit is Weber. Unit of flux is Weber or Tesla meter squared. Not even once they use Tesla meter squared. They normally use Weber. Okay, this is magnetic flux. Okay, the magnetic flux, the magnetic field strength and the area. You see the area have to be normal. If the area is not normal, then you have to find the normal component of the magnetic field to find the magnetic flux. Okay, you see here the magnetic flux BA cos theta. Okay, why cos theta? You see this diagram. The area is facing to the what direction? Like northwest direction. Okay, and the magnetic field is straight vertically down. So what do we do? We get the vertical component of the B. So that it's normal to the area. Then vertical component, how do you get a vertical component? This B we bring to the other side to make it normal, okay? Because the surface is like this. The B is attaching like this, original B. But we get this this component of the B. If this is theta, this B we brought here, it will be B cos theta, and the component, and times with the area, you get the flux. So BA cos theta is, what is theta? Theta is angle between the magnetic field strength and the normal line. That should be. Okay. So yes, now you tell me. You see this area. If this coil turn to in a what do you call, in a anti-clockwise direction, what happened to the flux? Flux drops or rise? And this area become more vertical. We turn it to anti-clockwise direction. What happened to the flux? Flux drops or rise? That means this area become more vertical. This area become more vertical. So this area we put it more vertical like this, more vertical. More vertical. That means we can say the angle get bigger. The angle get bigger. So therefore cos theta get smaller. So the flux drops. So when is the flux maximum? Flux is maximum when the area and the B is perfectly normal. Then the flux say to be maximum. Okay. If the area is vertical, the surface area is vertical, okay, and the B also vertical like this, so the flux becomes zero, no flux. Okay. So a flux passing through a N-turn. Let's say now you have an N-turn, you have number of N-turn. Magnetic field strength is horizontal. Okay. What is the flux? How much of flux pass through this coil? We call magnetic flux linkage. Linkage comes in when it has not one turn, it has an N-turn. If it N-turn, the magnetic flux is not only BA cos theta, but NBA. N is multiplied to get the total flux. It is called flux linkage. Okay, so one example about flux. Okay, check this diagram. The diagram shows a suspended rectangular coil free to turn about a vertical axis. The magnetic flux density between the N and S is 2.5 Tesla. So this is N, this is S, so it's 2.5 Tesla. The 2.5 Tesla, millitesla, sorry. If the area of the coil is 6 centimeters squared, this area of the coil is 6 centimeters squared, 6 centimeters squared. What is the maximum flux? What is the minimum flux through the coil as it turns? Okay, if I view from the top, this is south and here is north. Okay, let's say this is the AH, this is the B. So view from the top. When I view from the top, okay, say AB like this A, this B, this is the top view, plain view. This is the plain view. So tell me, if the AB like this, or when it turns, the AB might position like this, 1 or 2, the flux is maximum. The magnetic field is this way. Magnetic field is here. Tell me, one or two will create a maximum flux. Will be one, right? Because one, the area is like normal to the B. Normal to the B, the area going to be big. So the maximum flux happens when the AB is like this position, as shown like just now in the diagram. Minimum flux happens when it turns what angle? Anyone? What angle it turns? After what angle it turns, the flux becomes zero.
90 degrees.
90 degrees. Very good. 90 degrees. Okay, so how much is the flux? That's what calculated here. When the surface is normal to the B, theta actually zero. So maximum flux is BA cos theta. Theta is zero. So you get this flux, 1.5 times 10 power negative 6 Weber. And if after it turns 90 degrees, the flux become zero. Okay. So when you make one round, when the coil make one round, how many times the flux going to be zero? Let's say at the beginning it was vertically positioned, north. How many times it will be going to be zero? Flux going to be zero. At 90 degrees turning, after that, 270, right? Okay, from beginning to 270, you get another time flux become zero. Okay, so this is flux. What is flux? The product of magnetic field strength, normal to the surface area, and area. Okay, it's called flux. It's Weber. It's a scalar quantity. Okay. Okay, now comes to the law. Before we go to this, I need to do one question. Okay. So this is the word file. So electromagnetic first is magnetic flux. Magnetic flux is B cos theta. Okay. The one I introduced just now. Unit is Weber. Weber. Okay. Can you get me the answer for this? Okay. This is one example. This question. 1 minute. Give a try. Okay, so calculate the magnetic flux through this window. So this is the window. It was inch at AB. AB is the inch. So it was, the window is like this, and the magnetic field is just normal to the window. Okay. So what is flux produced here? So flux is V dot A cos theta. Here the theta is 90 degrees. It's 90 degrees. This here theta is 90 degrees. It's 90 degrees. Theta, if this is a surface, this is the magnetic field. Okay. The theta given is which one? Theta is this one. This is your theta. Okay, this is your theta. Sorry. Theta is 90. Theta is 0. Sorry, I made a mistake. Theta is not 90. 0 degrees. The angle given is angle from normal. This is your theta. Okay. So in this case, because the line is normal, so the theta is 0. And the theta is 0. So the flux is actually B dot A. So B here is the 1.8 times 10 power negative 4. Area is, of course, 60 times 85. Change to meter. Then you should be able to get this answer. Able to get this answer. But now, if this window, when you close it, let's say you turn it 90 degrees, then the flux is going to drop to 0. Okay, it will drop to 0 after it turn 90 degrees, about AB as the hinge. Okay, so this is magnetic flux. Okay, any questions so far about flux? Okay, so let me introduce the law. Okay, the law which governs the generator is Faraday's law. Okay, Faraday, I think you learn in chemistry, but in physics too, he is the founder of the law which makes how to have a strong generator. According to Faraday's law, states that the EMF induced in a circuit is directly proportional to the rate of change of magnetic flux linkage. So Faraday says the EMF induced is directly proportional to what? The EMF is directly proportional to the rate of changes of magnetic flux linkage. So the EMF is directly proportional to the rate of changes of magnetic flux linkage. This is flux linkage, so it should be BAN, flux linkage. B dot A dot N. Okay, we can put cos theta, cos theta. Okay, you want to get big EMF, you must change the flux faster, greater rate. Okay, just now, this coil, and the coil from flux how much? 1.5 times 10⁻⁶ dropped to 0. That means this body, there is a flux change. The flux change is actually the final flux minus the initial flux. Okay. Normally, Cambridge, they put it as a modulus. They take it as a positive answer. Okay. Flux change. Flux change means just final smaller than the initial, it become negative, but they take it as positive. Magnetic flux change over the time taken. So final flux 0 minus the initial flux is how much? Initial flux is this much, 1.5 times 10⁻⁶. You place here, divide by, let's say this turning 90 degrees happens in 2 seconds. Then this calculation gives you the voltage, the amount of voltage generated in this coil, in the conductor. Okay, the EMF produced in the conductor is directly proportional to the rate of changes of magnetic flux. Okay, the EMF induced where? In the conductor. Okay, in the conductor. So if it's a closed loop, the EMF going to result to a current flow. Current will start to flow. We get electricity. Okay. So that's Faraday's law. Faraday's law states that the EMF induced is directly proportional to the rate of changes of magnetic flux. Okay. So now the question is, for an EMF induced, there must be a change in magnetic flux. Magnetic flux must change. You know, the BAN value must change. You know, the question is, a change of magnetic flux linkage can be produced by one of the following. Okay. How do you can change the flux so that you get EMF? The first way to change the flux is moving the coil. Okay, move the coil. When you move the coil, let's say you have just now the turning. Just now you see the coil. The coil you are turning what? If you turn the coil, the flux will change, right? You see 1.5 times 10⁻⁶ becomes 0 because you are moving, you are turning it. So if you move the coil or you turn the coil, you get flux change, so you get EMF. Okay, that's one way. That's what happened in generator. In generator, the coil turning, flux of the generator, the coil changing, so the coil experience EMF. Or another way, don't move the coil, move the magnet, which is very, very rarely done. Move the magnet. That means what? Make the coil same, but the magnet at the side here, move the magnet, turn the magnet. When you move the magnet, also flux will change because the angle is changing, the theta will change. Okay, but very rare done, moving the magnet. Okay, so moving the coil or moving the magnet, you got flux change. Third is a very unique way, not moving anything, just change the current through the electromagnet. This also can create flux. Change the current through the electromagnet. Okay, I need to explain the third one. Okay, how changing current through the electromagnet can produce flux change? How we can change the flux? Okay, let me go back to the diagram. Okay, you see, you have a coil. You have a coil here. The coil produces a north pole here. You have another coil here. You have another coil here, in such that this is south. You place a rectangular coil here. You place a rectangular coil here. Okay. Later connected with the voltmeter. We have a voltmeter here. Rectangular coil. We place a rectangular coil, a fixed coil. So this is the area. The area. Okay. The question is, EMF induced is directly proportional to the rate of changes of flux, and the EMF, the flux is actually B dot A dot N, B dot A dot N dt. So EMF directly proportional to the rate of change of flux. So the third point, they say flux can be changed by changing the current here. If the current here changed, let's say this connected to alternating current, alternating source, alternating, the current is like changing up and down. So what happened? The magnetic field strength, which is coming out here, the magnetic field strength, which is directed downwards in this case, because north to south. Okay. So when the current change, when the current is changed, when the I changing, what will happen? The magnetic field strength will change. The field become weaker. If the current increases, the field become stronger. The field becomes stronger. I think you learn in your early studies, right? For a coil, if the current rises, the magnetic field is stronger. When the magnetic field gets stronger, what happened to this field line? Last time, let's say you got only four lines on this coil, 4 lines on the coil. Now you might have more stronger field line. The field line will get stronger. That means you have more magnetic, more field line in the area. So your flux will increase, because flux is what? Magnetic flux linkage B dot A dot N. The flux rises because what rises? The B rises. The B rises. Okay, the B rises. So that is the third way of creating EMF here. You get a EMF here later. You get a EMF here because flux is changing by changing the current in the electromagnet. This is the way done in the transformer. Transformer, last time the transformer, what is the function of transformer? Anyone? Changing the voltage, right? And the NS over NP goes to VS over VP. So the primary voltage VP, the secondary voltage VS. How the VP changed to VS? What is happening inside? The flux has been changed, and then the secondary voltage is generated. Okay. For example, you see the primary coil, a current is sent through the primary coil. Okay. So what happened? The core turned to become magnet. The core turned to become magnet. Okay. So when the core turned to become magnet, what happened? The primary coil is connected to alternating AC supply, supplied to the AC supply. So AC supply current changed. So the magnetic field strength in the core changes. Therefore, what happened? The flux is changing in the secondary coil, because you see the secondary coil is linked to the magnetic field. The magnetic field is changing. The secondary coil flux is changing. The secondary flux is changing. Therefore, a new EMF will be induced in the secondary coil. We label it as Vs. So in this transformer, how voltage is EMF is created? By changing the B. How B has been changed? By the current has been changed. By the current flow in the electromagnet is changed. And this is another way of producing EMF. Any question from this? So Try to understand this 3 point. Faraday's law says that EMF induced directly proportional to the rate of changes of magnetic flux. Okay, you can change the magnetic flux by 3 ways. Okay, understand the 3 ways. Moving the coil, moving the magnet, or the third one, change the current. Change the current also can produce a change in flux. Okay. Okay. Faraday said EMF is proportional to d psi over dt, but he never mentioned it's negative. Negative is told by another scientist. That's another law, next law. Okay, first let's just understand the Faraday's law first. Okay, now. So that's about Faraday's law. Now, the second law, last law in this topic is Lenz's law. Okay, what Lenz's law stated? Okay, Lenz's law stated that the direction of the induced EMF is such as to cause effect to oppose the change producing it. What does this mean? The direction of the EMF. For example, you see this the first diagram. You see the first diagram. Okay, the magnet is going in. The magnet is going in. And the magnet is going in. There is a coil at the bottom. When the magnet is moving in, flux of the coil rising or decreasing? Anyone? And the magnet is moved into the coil. The flux in this coil increasing or decreasing? Anyone? What is flux? Flux is B dot A, number of turns line. Okay, flux linkage. When this magnet goes down, any factor rising? What is rising? Anyone? When the magnet moves down, which quantity changing? N, the number of turns. The number of turns of the coil is fixed, never changed. A, the area of the coil does not change, is still the same. Okay, what is changing when the magnet is moving closer? The B is increasing. The magnetic field strength is increasing because the North Pole is getting closer. The North Pole getting closer, the magnetic field strength on this area increases. When the magnetic field strength increases, what happens to the flux here on the coil? Rises. The flux here rises. Okay. So when the flux is changing, the coil experiences change in flux. Okay. So the conductor, this is your conductor. The conductor will induce, according to Faraday's law, must induce what? Must induce EMF. But this EMF, is it make the current to flow clockwise, anti-clockwise, or clockwise? Which direction the current should flow? The direction of the current flow is explained by this law, Lenz's law. Okay. Now we understand why in this diagram the current they put in the current flows is a anti-clockwise direction. Why the current flow is anti-clockwise direction? Okay, according to the Lenz law states what? The direction of the induced EMF is such as it opposes the change producing it. It opposes. Oppose means what? The current is flow in such a way that to oppose, to be against the change producing it. What type of change happens here? What type of change happens here? The current is against to the change. That's Lenz's law. What type of change happens here? Change means change to the flux. What type of change happens to the flux? Flux rises or flux decreases? And the magnet moving closer. The flux is rises. Okay, flux rises. Flux is rises. So the current will try to oppose this change. So how we can oppose it? If flux is rises, the current will flow such a way that try to decrease this flux. You don't want this change. You don't want this flux to rise. Because not to say the flux to rise. You don't like the change. The change happen here is flux is rising. So you stop the rise. How we can stop the rise? A current is created in a clockwise direction. In the anti-clockwise direction. Why the current in the anti-clockwise direction can stop this change? How? Anyone? How flowing anti-clockwise direction, the flux can be stopped rising? Because if the current flow in anti-clockwise direction, the current going to produce a its own magnetic field. The magnetic field produced by the current is directing upwards or downwards. You see, clockwise direction. If it's clockwise direction, use your right hand grip rule. Okay, class, use your right hand grip rule. Your finger is your current. Your thumb is your north pole. Right? Use your right hand grip rule. Right hand, don't use left. So put your finger around the coil. Okay, around the coil. So put your finger here. This is your finger. Surround it. Yeah, your finger like this. And your thumb going to point where? Upward or downward? Thumb going to point upwards. So the wire, right, the current flow produces a magnetic field upwards to oppose the original magnetic field. The original magnetic field is where? Downwards. So he opposed the original magnetic field. He tried to oppose the magnetic field. So when it opposed the magnetic field, what happened? The flux, which is increasing, stop rising. Cannot rise. Difficult for it to rise. Because what? The B, right? The B initially rise by the magnet. Okay. The current flow such a way the B is decreases again. How the B is decreases again? Because the current create another magnetic field opposing the original magnetic field. So this is based on Lenz's law. Lenz's law. The direction of the current flow, the direction of the EMF induced is such as to oppose the change which produces it. In other words, it's against the creator. It's against the creator. It don't like to be created. If it's come out, the current comes out, you can oppose the change. What type of change here? Either flux is rising means the current will try to decrease the flux. If the flux is decreasing means it will rise the flux. It opposes the change. Okay, don't put in your mind like it opposes the increase in flux. Not it opposes the change. If it increases, it's try to slow down. If it decreases, it's try to increase this back. That's Lenz's law. Okay. So we try to explain the second diagram. Use the Lenz's law. Try to understand the second diagram. Okay. I think better I go to the whiteboard to explain this. This is the core of this topic. Okay. Again. So now let's say you have a magnet. South here, north here. You have a coil. You have a coil here. Coil here. It's a close. Okay. You move the magnet up. Move the magnet up. Tell me, the current flows here. The current flow in the coil. Is it going to be clockwise or anti-clockwise? Use your Lenz's law. Use your Lenz's law. The current flow here. Is it going to be clockwise or the current flow going to be anti-clockwise?
Anti-clockwise.
So anti-clockwise. Okay, let's see. Is it anti-clockwise? So you choose this one. Okay, let's see. Okay. First, you have to check when the magnet goes up, the magnetic field in the coil become smaller. So what happened to the flux in the coil? Decreases or increases? The flux B dot A dot N, because the magnet move away, the B gets smaller, so flux is decreasing. Okay, flux is decreasing. So the current must move, the induced current must move such a way that need to rise the magnetic field back. Okay, need to rise the magnetic field back. The original magnetic field is which direction? Because south, the magnetic field is upwards. Magnetic field is upwards. Okay, so the current should flow such a way that to increase this magnetic field strength. So the current must create a magnetic field same direction or oppose the original direction. You must increase the magnetic field back. So the current must produces a magnetic field same direction with the original magnetic field. So use the right hand grip rule again. the current will flow clockwise, anti-clockwise should give the magnetic field upwards. Okay, so use your right hand grip rule. This your, I think your fingers, I think your thumb should point upwards. So because we want the magnetic field upwards, we want the magnetic field upwards. So the current should flow anti-clockwise. Current should flow anti-clockwise. This is Lenz's law. Okay, the magnet move up causes the coil to experience changes in magnetic field strength, causes the changes in magnetic flux linkage. Therefore, EMF is induced. But EMF will lead to current flow if it's a closed circuit. But the direction of the current flow is determined by the what type of change happens here. If the flux is decreasing, the current will start to rise the flux by producing a magnetic field same direction to the original magnetic field. Okay, that's why it's anti-clockwise. Okay. Okay, another one. Let's say you have a north here and you have a coil here again. The magnet is moving up now. So which direction the current flow here? Anti-clockwise or clockwise? Give a try, everyone. So the north pole is moving upwards. So when the north pole is moving upwards, the coil experience changes in magnetic flux linkage. EMF will be induced. So current will flow anti-clockwise or clockwise?
Anti-clockwise.
This is also anti-clockwise. Okay, so let's check again. So flux is B is dropping or rising, move away, B is dropping. So flux is dropping, flux is dropping. So the magnetic field here is downwards. The magnetic field is downwards. The original magnetic field, okay.
We know clockwise.
Clockwise, okay. The current must flow in such a way that to rise the flux, you need to rise the flux because flux is dropping. So current also must produce a magnetic field strength the same direction. Okay, so you use a right hand grip rule. How the current should flow? The thumb should point down, your finger, I think, this way. So current should be clockwise. Yes, it should be clockwise. In exam, they will ask you to identify the direction of the current. So this is Lenz's law. Okay, this is Lenz's law. Okay. You see, in your classroom, okay, in your classroom, okay, you have the door. This is the door. Okay, you have tables here at the side. Okay, you have the door. Okay, the door knob. Okay, let's say the door is made of aluminium frame. Let's say made of an aluminium frame. Made of aluminium frame. The door is closed now. Okay, the door is closed now. Okay, let's say Earth has its own magnetic field. Let's say this position is pointed at the north pole of the Earth. So let's say the magnetic field is into the door, cross. The magnetic field is into the door. Okay. Okay. Now let me put the age. The age is okay. This is the age A, B, C, D. The door frame was made of aluminum. That means it's a metal. Okay. Now the thing is, someone, let's say, you open the door. Okay, you open the door. So you open the door. Okay, now because you open the door, the frame of the door experience changes in flux. Magnetic flux of the frame is changing. Okay. Okay, now tell me, when you open the door, the frame of the door will experience changes in flux. Therefore, EMF will be induced based on Faraday's law. Tell me, according to the Lenz law, the current will flow clock ABCD. Oh yeah, current will flow ABCD direction or the other way around, DCBA. DCBA, sorry. One or two. Use your Lenz's law. Explain to me when you open the door. Okay, first, sorry, let me change. Okay, first, what you must think is when the door is open, flux is dropping or rising? when door is open, flux is dropping or rising? P dot A dot N. Flux is dropping or rising? The area faced by the magnetic field strength. The area, this is the area, this is the area. This is the area.
Dropping.
Dropping. So flux is dropping. So flux is dropping. Okay, when the flux dropping, because flux is changing, EMF is induced. So the current must try to oppose this change. It will oppose this change. The change is flux is dropping. So it will try to rise the flux. So the current will flow ABCD or the other way around. So it's going to create, the current going to create a magnetic field same direction to the original field, or oppose the original field. Same direction to the original field. So the current also must produces a magnetic field into the door. So if it's into the door, use your current your right hand grip rule. Point the thumb into the door. Right hand grip rule. Don't go for the left. Right hand grip rule. Thumb into the door. So tell me the current flow must be ABCD. Should flow in a clockwise direction. Okay. So it's very difficult. You point the thumb and your finger like this, right? Your finger like this, your thumb is this way. So I think your finger will be this way, right? Pointing this way. So your current should flow ABCD. Up ABCD. So you generate a current. Okay. It's a good idea. Okay. So any questions from you? No questions, Okay, this is the core part of this topic. You need to understand this to understand everything. Okay, so I hope you understand the other remaining diagram. Let me explain another one only, the D part. You see the D part. The velocities move up, the magnetic field in the coil drops. Okay, so the current must move such a way that to rise the magnetic field strength, so that the flux need to be increased because flux is dropping. But the field of this, because south pole at the bottom, the field is upwards. The field is upwards. Okay, the field is upwards. The field is upwards, and the field get weaker. So the current must produce this another field to enhance the field. Okay, enhance the field. So the current must produce this field upwards. So use the right hand grip rule. The current will flow in this way. The as shown here should flow in a anti-clockwise direction. Create another magnetic field upwards to decrease the change. Okay. So in other words, the Lenz's law, the current induced here is like inertia. Inertia, you know, right? Inertia oppose the change of state of motion, right? You don't like any change to your movement. It doesn't mean you don't like movement. You don't like changes in the movement. You can keep on moving, but if you stop, inertia going to act on you. Or if you are in stationary, if you start to move, inertia going to stop you from moving. The same idea here. The induced current oppose the change. Okay, the type of change happen here is the flux change. Okay. Okay. Lenz's law is actually made of conservation, based on conservation of energy. Okay. The Lenz's law is statement of law of conservation of energy. Because when you move inside, the coil turns right. If you north pole going in, the current will make north pole here. It's going to oppose you, so you feel a repulsive force from the coil. So, but you are still moving to the left, so you do work. You do work against the repulsive force. So the work you've done to overcome the repulsive force is turned to become electrical energy. Okay. So Lenz's law is based on conservation of energy, actually. Okay. Okay, class. So just another 2 or 3 minutes, we stop. But try to understand what you learned today. This one question. Look at this question. Try to look at the solution. Hope you understand. 1 minute for you. Okay, so I hope you got some idea. Uniform flux density, this much of this is the field strength. Small coil area was placed in between. It has a 250 turns. This is your A, this is your N, this is your B, which is with its plane normal to the magnetic field. So the plane is normal to the magnetic field. The coil is withdrawn from the field in a time of 0.26 seconds. Oh, you have a coil, magnetic field. Okay, yes, a magnetic field. But here no magnetic field. The coil is totally moved to the right, so that it withdrawn from the field, totally withdrawn from the field. So this is the first case, and this is the second case. So this is the first flux, and this is the second flux. Tell me, when the coil is moved away from the magnetic field, the flux drops or rise? Flux drops, right? You go to a region where no magnetic field now, B is 0. So the flux at 2 will be 0 because no magnetic field at all. No magnetic field at all. Okay, the question asking, the magnetic flux through the coil when it is between the poles of the magnet. What is the original magnetic field? The flux 1. So B cos theta. But cos theta, we take it as 0 because it's like this vertically, this is the surface. So the angle there is 0. This is the angle which is 0. So 5.2 times 10 power negative 50 and negative 5, sorry. Change in flux. The final flux we know 0 minus the original flux is this one, but need to multiply by the 250 because flux linkage. Flux linkage. Whenever they say the word linkage means you need to multiply with the n. Okay. If they say magnetic flux, no need to multiply with the n. Okay, magnetic flux linkage, you need to multiply with the n. This is the magnetic flux linkage. Okay, negative sign indicates that the flux is decreasing. Okay. So third, what is the average induced EMF in the coil is being withdrawn? Okay. So according to Faraday's law, the EMF induced is the rate of changes of flux. Flux change is 1.3 times 10 power negative 5. As I said, Cambridge, although the change you got negative, normally the changes in flux is actually final minus initial, right? Okay. Cambridge, normally whatever number you got, maybe you get a negative 5 Weber. When they calculate the EMF, they just put it as 5 Weber. They take it as positive. Even changes in magnetic flux also, they put it as 5 Weber. Okay, like a modulus. They take it as big minus small. That's what happened here. The magnetic flux divided by the time 0.26, 0.05 volt should be induced in this frame, which led to a current flow. Okay, any question from this slide? Okay, so hope you understand. Okay, so just part A. I don't want to do part B, only part A. Give me the answer only for part A. Calculate, tell me the answer. Only part A, no need to part B. So the coil has been shifted, moved away, has been displaced away totally from out of the magnetic field. Okay, jerked to the left. And that means the flux dropping to 0, and totally out, the flux becomes 0. Okay, so they're asking what is the EMF induced in the rectangular coil. So according to Faraday's law, EMF is rate of changes of magnetic flux. Final flux minus initial flux modulus the changes over the time give you the EMF. So what is the final flux? We know 0. Initial flux, how much? Initial flux. So initial flux is B dot A dot N, right? B dot A dot N will give you the initial flux. Sorry, not final, initial flux. B how much? B we know is 2.5. A is the area, 10 times 12, but change to meter, and N is the 30. Okay. So yeah, so that's the A answer. You see the A answer. So, oh yeah, so negative. So I forgot to mention this. This negative is due to Lenz. Lenz said the EMF always oppose the movement, always oppose the EMF induced always oppose the movement. So he put negative. So negative is from Lenz's law. But Cambridge, what they're going to put? They're going to put like this EMF. They're going to say changes in flux over time. A flux change, normally they do, as I always, final minus initial, right? Okay. But it's like, you can imagine like it's a modulus law. Even you don't need to put modulus. Okay. You just say final minus initial. If it's negative, make it as positive. Okay. So yeah. So BAN divided by the time, you get the voltage. It's 1.8 volt. Okay. Cambridge, what do you do? The changes of flux, right? Final minus initial. If you get negative, let's say you got negative 10 Weber, here you put 10 Weber only, positive, and the time. Okay, the time of movement, in this case 0.5. Then you get the voltage generated. Okay. Okay.
So what if it's positive? Then just times negative 1.
Why it become positive? Okay. In actual rule, this is the working has been shown. Okay, actual rule, you see, outside they put negative because of Lenz's law. Inside they always follow final flux minus the initial flux. Okay, but in Cambridge, in the mark scheme, in the Cambridge, let's say this question asked in Cambridge, what they put, they always put, they never put final minus initial, over time. Here the final minus initial, they always assume it as, they won't put final minus initial, they just put changes of flux, and they always put it as positive. They always take it as positive. Okay, take it as positive. So what my advice is, at the top you do, you calculate the flux first. You calculate the flux first. Final flux minus initial flux first. Let's say you got negative 10 Weber. When you go and put in the EMF, right, the changes in flux, you put it as 10 Weber. You make it positive. So understand? So you always go final minus initial for the changes in flux. You got a negative answer, you just make it as positive. So the positive must be the answer written on the answer column. Okay? Understand? Okay, any question?
So basically, EMF is always positive.
EMF always positive in Cambridge. So we follow Cambridge now. So we always make it positive. The changes in flux is always positive. Okay? Any question? Okay, class. So I stop here. So today, this is our lessons today.
All right. Thank you, sir.
Okay, see you tomorrow. Yeah.
See you tomorrow.